Imagine a master chef trying to finalize a new soup recipe. They need to figure out how much salt and spice to add, so they take a quick spoonful, taste it, and decide what to change. But there is a huge risk in relying on just that one spoonful, or handing it to just one taste tester. Individual preferences vary wildly, and one person's opinion rarely reflects what the general public actually wants. To get the recipe right, the chef needs to serve the entire dining room. In our world, we call that total number of customers M. This group represents our complete dataset, where every customer is a different training example. The chef gathers feedback from all M customers, adds it all together, and calculates the overall average preference. Training in artificial intelligence follows the same logic. It updates its internal rules based on the average error calculated across every single training example we provide. This chart shows how we express that average mathematically. At the top, we have the total cost function, written as J. It is the sum of all the individual mistakes made across our examples, divided by M to give us a true average. The second part of the image shows how we calculate the recipe adjustments. We look at the derivative, which is just a measurement of how much our total error changes if we nudge a setting like salt or spice. We find these individual nudges for every example, add them up, and divide by M. Knowing the math is one thing, but a computer needs a practical, step-by-step process to actually gather all of this feedback. We have to write a set of instructions it can follow. This code shows that process in action. Before the restaurant even opens, we start our tallies at 0. Looking at the top line, we initialize our total cost J and our specific parameter nudges to 0, so we can start with a clean slate. Dropping down a line, we see our for loop. This instruction tells the computer to visit every single example, from customer 1 all the way to customer M. For each one, it calculates a specific prediction and measures the error. Inside that loop, the actual accumulation happens. The computer calculates the specific nudge needed for feature 1, like our salt, and feature 2, our spice. It takes those individual opinions and adds them to our running tallies. Finally, look at the bottom left of this block. Once the loop finishes visiting every table, we take those massive running tallies and divide them by M. This gives us the exact average feedback across the entire dataset. This explicit looping process takes the theoretical math of gradient descent and turns it into a practical, programmable accumulator. Over on the right side of this image, we see the very last step. We subtract those newly calculated average nudges from our current recipe and update our parameters. You now know the complete logic required to train an AI model that sorts data into categories, like deciding whether a recipe is a success or a failure, across millions of examples. But think about what happens when our restaurant scales up. What if we are running a global franchise with 10 million customers and 500 different ingredients? Explicit for loops have a major flaw. They force the computer to handle things one at a time. The system must finish with customer 1 before moving to customer 2. Every calculation must wait for the previous one to finish, creating a massive backlog. Modern machine learning requires us to process incredibly large data sets. When you are dealing with millions of data points, forcing your computer to process them one by one takes too much time, which makes the algorithm impractical. To fix this, look at the green handwriting at the bottom of the screen. Vectorization is a programming technique that allows a computer to grab those millions of data points and process them all at once, completely bypassing the need for a loop. Writing out a loop is the best way to understand the mechanics of how an AI learns. But to build models that can handle the scale of the real world, mastering vectorization is your essential next step.